record. And we are going to start sharing screen. Okay, so we will continue our discussion on AVL tree. Is it last class? We discussed AVL tree. Did we do quiz last class, Tuesday?
Yeah, we did.
Oh, we already did. Okay. Then probably let's just review together. Okay. And AVL tree. So who still remember what's the difference between AVL tree and the general binary search tree?
The AVL tree has to be balanced.
Yes, very good. Okay, it needed to be balanced. Okay. And the binary, there is no such requirement. Okay. So AVL tree is a self-balanced binary tree. Okay. And then when we discuss it's self-balanced, is it? So the advantage, and if you recall previous, we also learned set and map, is it? And when we learn set and map, we said in Java, they also have tree set and the tree map concept, is it? And basically, and they also have hash set and the hash map, is it? And the difference between the tree one and the hash one, previously, I remember we kind of discussed, is it? And for tree one, because internally in Java, they are not AVL, okay, some other kind of, but it's some balanced tree. Binary tree, is it? And for hash, they using what hash table concept, is it, to implement. And so if you still recall the difference between these two, the advantage, so balanced tree, so it's kind of like a AVL tree, okay, AVL tree. So anyway, so it's balanced. So the advantage for the tree implementation is what? Is to maintain order, is it? So ascending order, so we can also call it sorting order. Is it? That's its advantage, is it? So like if your application, is it, has a lot of operations that depends on the order, then it's recommended that you use balanced tree data structure. Is that bad? But if disadvantage, because then in this case, we said the time complexity is log 2n, is it? And the disadvantage is compared with the hashing as a lookup is slow. Is it slower than hashing? Is it because the hashing is just order of 1? Is it? And in our next unit, when we learn hashing, you will see why it's order. This is just generally speaking, okay? Okay, so that's the advantage, okay? Because if you involve a lot of operations, your application involves a lot of operations that's more related with need to follow certain ascending or descending order, is it? Then you can choose the tree data structure. Okay. Okay, so that's the idea about the advantage.
Yeah,
And
excuse me.
Yes,
what
please.
is different between hash set and hash table?
Hash set.
Yeah.
Hash table, yes. That's a major difference between set and the general. We can see table, you can think about like array, list, those kind of linear data structure, is it? So that's linear data structure, or ADT, abstract data type, is it? Set is what? Set is not linear. Is it, generally speaking, its main feature is what? Its uniqueness. Is it is unique? And then for hash set, you can't just drop it in. So in math, is it we always draw set like a circle, is it? And then everything in it, but it's unique. Unique. And for all of this, they allow repetitive items. So they don't have that requirement for unique. That makes sense?
Yes. So they are both have key value pair.
No. Key value pair is map. Map, only map has
yes.
key. Don't get confused, okay?
So sorry.
Yeah. Okay, that's okay. Only map has key value pair. Don't get this of this confused. Okay, so that's a different data structure. Okay, so if you want to keep uniqueness, you use set. Okay, and the map, the advantage is it has key, and the key helps look up. So speed up, look up. Is it? So, but it still depends on which one you choose. Is it? And if you use a hash map, then it's order of 1. Is it? If you use tree map, it's generally it's still log 2n. Okay, but generally speaking, if you have a lot of key value pair, and all this part, we think is just 1. No key, it's all value. Is it? 1 item, single item, not like this. You have basically kind of 2 parts, key part and the value part. Okay, don't get off this confused. Okay, and generally speaking, map, the advantages is look up. That's why in a lot of other data structures, they also call dictionary. The dictionary, you look up something, is it? Okay, very good question. Okay, what I just said, okay, AVL tree, is that AVL tree? Okay, it's balanced. Okay, AVL tree, and yesterday we discussed different techniques, is it, to balance. And also be careful, we here said balance a node. So you need to node by node balance, basically. Okay, you need to balance a node. So whenever you do insert, you need to kind of balance. Whenever you do delete, you need to do balance. But of course, not always. Okay, that's what Alex, very good point yesterday, okay, mentioned. Yeah, some boundary cases that we don't need to balance. But generally speaking, we need to balance a node. Okay, balance a node. And balance a node, then yesterday we discussed 4 cases. That, and generally speaking, it's what? Right. And is it and right, left, and left. Is it right heavy? Is it right heavy or left heavy? Is it the other one is right? Oh, I should write here. Right, left. Is it the other one is left, right? Is it? But both are considered as right heavy. Is it? And we have this two. And for right to right, just involve what? One rotation. Is it that one rotation is what? It's a left. I remember it's a left rotation. And if this case, right left, it involves two rotation. Is it right rotation, then followed by a left rotation to balance the node? Is it similar for the left heavy cases? Okay, so that's what we discussed yesterday about the techniques to balance a node. And then we also said that whenever you do insert or delete, generally speaking, it's along the path. Is it either insert or delete? And the path, all nodes along the path, okay, we need to do balancing. Is it needed to balance, and also involves the update heights. Is it to update heights? And and whenever we discuss this, we have that word called balance factor. The balance factor for AVL tree, balance factor can only be what? -1, 0, or 1. The balance factor is right subtree, left subtree, the offset between the height that of the left subtree and the right subtree regarding the height. So that's all of the concept. Okay. And today, let's take a look. This is just my version of AVL tree. Okay, it's not the best performance. Okay, it may not be the best performance. My version. Okay, and if you have better one, please let me know. Okay. And my version, I implemented like this, okay? Because anyway, it involves comparison, that it's a binary search tree, it's a base, okay? So what over here I do for the generic, I let it extend comparable. And previously, we also see some other example, and also with Java collection framework design, it's not, that's not the only way, okay? The other way, and I haven't tried, okay, for the other way. Other implementation is based on comparator interface. That's more flexible, okay? This is more flexible. That's why if you take a look at Java collection framework, a lot of method is it they take some comparator as the argument type. Okay. So anyway, so this is my version. Okay, I haven't tried with the other version. So maybe in summer I will find out I will write my comparator version. So anyway, so let's just take a look at this version. And I based on this design of our binary search tree, okay, my binary search tree. And so we still have the bin node. Okay, bin node, you have data, you have left subtree, right subtree, so nothing changed here, okay. But if you recall, we need to consider balance. Is it balance is based on height? So this is the key we add for AVL tree. So we add a new instance variable. It's regarding height. Okay, regarding height of that specific node. Okay, and here's the constructor. The default one just initial height as 0. And the second one is you can pass in certain height, is it? And then you can initialize height with the specified height, okay? Okay, so that's the idea. And also over here, I put this bin node as static nested class, is it? So bin node is a static nested class. Okay, and if it's not static, a lot of time you also call it inner class. Inner class, as the previous we learned, is it? And we also learn anonymous inner class, is it? All of those concepts. And the static one, okay, so this is static one. And the static one, then why we designed as static one is as then it prevent you to access the outer class members. Okay, so if you recall previous last semester we discussed this concept in CS2. Okay. So anyway, so this is a inner class. Okay, and then for the AVL tree still, we only have that single instance variable, the root node. Okay, root node, that's it. Nothing changed. And for AVL trees, the constructor, we just let the root be a null. So start with empty tree. Okay, so this is pretty straightforward, nothing new, okay. And is empty also pretty straightforward, is it? And because here involves hide, is it? So we also have a method called hide to give you, this is a tree hide. Tree hide. Okay, so that's why over here it calls another function, but that's a private utility function. Utility method. Yeah, in Java it's always called method. Okay, and it's going to call the other method, hide, and it takes some node, is it? And what it get is if the node is a null node, it's a null, then it's -1. Otherwise, you just return the node's hide. Okay, so that's how this, because why? Because it also considers the empty tree cases. That's why we have this, okay. But anyway, so this is a utility method. Hi, that's too very straightforward. And for search, nothing changed. If you take a look, compare with our binary search tree, they start at root node, you either go to left or you go to right, is it? So nothing new here, okay. Exactly same as binary search tree. Okay, and then this is new, balance factor. Okay, we also want to know each node's balance factor because we need to balance node that after we do insert and delete, is it? So every insert or delete operation, is it, leads to what? Leads to balance node. Is it? Leads node balancing. Is it? Leads node balancing. And the node balancing counts on what? Counts on balance factor. Is it? Nodes balance factor. So that's why we needed to know the nodes factor. And how do we do that? Yeah, it's just a difference between the left subtree's height and the right subtree's height. Okay, and the different our textbook, I don't recall, okay, if it's the same as my definition, okay, but some other programmers, they may define different. They may use right minus left. Okay, so that doesn't matter, but you need to make it consistent for your tree. Okay, for the whole tree definition. So what over here, because it involves negative or positive, right rotation or left rotation. So what I here define, textbook may be different, okay? I don't recall, okay? But anyway, this is not mandatory. I define it as left the height minus right the height. Okay, that's what I defined for the balance factor. Okay, that's balance factor. It's easy to understand, is it? Okay, so here is the idea about right rotation and left rotation, is it? Let's see how the best to explain the code. Let me see, okay. If I can have more space. I cannot have more space. And maybe, let's see. Because I want to draw the tree so that then you can read the code more clear. Maybe just like this, okay. Let's first draw, this is right rotation, is it? Involves with right rotation. Rotate right, okay. Rotate right. Let me see my notes. So probably, let's see, this case. So let's consider this, A, and then B, is it? And here we have T4, that after B, then we have C here. And here is that T1. And here we have T2 and T. We consider this two cases, okay? Rotate twice. Let's see if this is the case, okay? So we consider node A. As then we said it's going to do right rotate. Is that right? And let's see the other case is A, then we have B, and then I have C. That here is the tree T4, and here we have that T3, and here we have T1 and T2. Is it? And we do right rotation. Is it? And when we do right rotation, we said we let B take A's left. Take A. So we are going to rotate B up. Is it? Rotate B up. A's left. A's left. Hold on. Okay, let me. A's left is. A's left, then take B's right. Okay, yeah, that's right. Okay, so here let's take a look. So rotate right. Okay, rotate right. What we are going to get is B going to move to up, as a move up, and then move A down. A down, is it? And the A's original tree T4 still keep here, is it? And the B's right. This is B's right, is it? B's right is T3, and it will go with what? A's left. So T3, is it? So this is correct. Is it this part we finish? Is it we finish? And then B as A's left. So A's left is this part, is it? And B, we initially assign B will take, and then let's see, B's left is not changed. It's still C. It is still C. And here is T1 and T2. As it is T1, T2. So we update, then we update B's right. So B's right we update, is it? And A's left we also update, is it? So we update both. B's right we update and A's left, yeah. So we update this part. So this part works with moving up and A moving down, is it? But you cannot just stop here, is it? Because you move A up and move A down and move B up. So that's why both height also need to be updated. Does it need to be updated? So the update of the height is based on what? It's based on A's left and A's right. Is it? You compare, is it? And you pick the larger one. Is it a larger one? So if A's left is larger, is greater than A's right, then you will take A's left's height. We just call the height method. Is it? And A's height then should be 1 plus its subtree. Is it? So that's how we update A's height. And the same thing for B's height. We also need to update. Is it? We also need to update. And so after you do, after you move B up and move A down, and this is a special case. Okay, special case if it is a root node, then you need to, don't forget to reset the root node to B, okay. Okay, so that's rotate right. And after we rotate right, the new A's location node becomes B, is it? So what rotate A will return? It's return node B, the new kind of root node for this unbalanced subtree. Okay, basically in this case, for this new balanced subtree, okay. So we return B, okay, we return B. So that's this case. And if we do this case, because anyway, this case will first be converted to this case, but it's changed to C. And then you're still going to do the right rotate. So over here, we consider the right rotate for this method. And then let's take a look at the left rotate, okay. Okay, then for left rotate, the tree, let's draw it, okay. So the tree, we have both case. This case involves the left rotate, B, and then here is C, is it? And here is T4. And here we have T2 and T3. Here is T1. Okay, so we are going to do left rotate. But first, that's the first rotate, that's the second. But anyway, after it involves left rotation. And the other case is the original case. So we have A, and we have T1, then we have B, and then we have C, is it? And we have T3 and T4. And over here we have T2, is it? And we are going to do right rotation, is it? And the right rotation is to bring B up and A down, is it? And so it's going to bring B up, and this C part is still the same, nothing changed, is it? And for B, then over here, you're going to bring A down, is it? Bring A down, and A initially has T1, is it? And B initially has T2, so it's going to move to A's subtree, is it? So you're going to move this also. Okay, so let's see. So A's right is B's left. As B's left is T2. And you give it to A's right. As A's right. And then B's left. So this is new B's left part. As you assign it to B's left. Okay. And also be careful about the order. Okay. We don't change the order. Okay, so this taken care of the rotation part, and then similar, you need to update the height. Is it? And after you update the height, and if it's a root node, you need to reset the root node to node B. Okay. Okay, so that's rotate left. Okay, so we discuss both left rotation and right rotation, and then what next? Let's see the balance. Okay, balance node. Balance node, the first case is if balance factor is -1, then what is that case? So that's the that's a right case, is it? So let's see, okay. So we have this A, and then here we have that T1, is it? And then we have B, and then we have C. Over here we have T2, and here is T3, T4, is it? Okay, so this balance factor, because over here we have 2 more, is that we assuming all of the other are balanced. So definitely you can see. So the balance factor is -2. -2, then it's meet this condition. Is it? Meet this condition, what we do? We do left rotate. Is it? We do left rotate. Left rotate, do you recall what it returns? That left rotate, it always return B. Is it? And did you see, initially you balance A, but then you assign B to A. Is it? So it's changed to B. Is it changed to, and also it return. What it returns B. Is this? So after you call the balance, it's always return B. Is it? It returns B. And so this is, so if this is less than, then you call rotate. But that's regarding this case, is it? We haven't discussed the other case. The other case is A, and then over here we have B, is it? But C is on the left. That's C, is it? And here we have T4. And here we have T2, T3, is it? And here we have T1, is it? And here it says balance fact. You also need to consider this case. So this is B, is it? So A's right basically is B, is it? And B in this case, it's greater than 0. So it's 1 in this case, is it? And if that's the case, then you need to do rotate, is it? And we do right rotate. And we do right rotate is we can get the tree as A, and then C, is it? After C, it's B, is it? And the C, then it's left, it's still keep as T2, is it? And the B is going to be updated, then here it's T4, is it? T3 is here, that's T3, is it? So T3 is going to be moved, is it? So anyway, let's take a look, okay? So A's right anyway is B, is it? And what you are going to do, you are going A's right, so this is B, is right. So you are going to assign assign B to what you call rotate A's left. Is it A's left is what? Is C. Is it is A, oh no, A's right, I'm sorry, A's right is B. Is it? You rotate around B. Is it? And we do right rotate B, what we get? We get C. Is it? We get C. Is it? That's why did you see it says A's right change it to C. Is it? So this part taken care of. Is it taken care of completely? And then you do another left rotate regarding A. Is it? So this part taken care of both cases, case 1 and case 2. That both cases are taken care of. And this else if part, similar. Okay, so it's taken care of both of left and right left. Is it? Or left right? Left to right, both of the other case. Okay, similar as what we just discussed here. So anyway, so this method balance then is going to balance that single node. Okay, so that's what this part means, this method. And then next, let's see. What next is, if you recall, whenever we do some insertion, okay, so how about let's see, so the other example, suppose 55, okay, let's just redraw that tree, 40, and here we have 42, and here we have 38, is it? And 39, is it? And here is 62, I believe, 62. Anyway, something, is it? And when yesterday we said like insert 35, is it? I will draw with a different color. So just insert. Is that we insert 35. When we insert 35, you will follow the path. As you will follow the path. And then yesterday we said after you insert, and of course in this case, because all of the nodes are balanced, so there is no balance involved. But suppose if you insert, let's see, some other number, 41, let's go to here, that's not going to, maybe assuming you are allowed to insert like 39.5 something, is it? If you insert here, then it involves balance, is it? Then you need to balance 38, is it? And the path is going to be along, this is a path, is it? And how do you record all nodes along the path? Is it? We need to record that, is it? So over here, I pick array list of the bin node to record the path. Okay, to record the path. That's what this update path method means, okay? And here is along the path, which node, okay? So the location, okay, of that node. So I'm going to start updating from this number, okay? So they over here, it's also bottom up. Okay, whenever you update height, you need to do bottom up, is it? Not top down, is it? Because when bottom node height change, it impact the upper one, is it? So child nodes height, child's nodes hide, updated, then definitely it will lead to parent node, hide, update. Is it? Definitely this two. So that's why it's bottom up, okay? Because it's bottom up, so that's why we loop from K to 0. When it's 0, it's a root node. Is it? Root node. And because it's an array list, so we can get each node out. Is it? And after we get that specific node out, then it's similar. Whenever you do height updating, as always, you find the left and the right subtree. Is it based on the larger one? Is it? And then you add one. Is it? Then you update the height. Okay. So in this case, every node is along the path, starting from wherever you specify, and its height is going to be updated. Okay. So that's this method. Okay, and then you update the height. That's not enough, is it? And we also need to balance all of the nodes, is it? Along the path. That's why here I provide a method I call balance path. Balance path, basically it's balance all nodes along the path. And the path is going to be recorded by an array list. Okay, and when we do balance, same thing. We start at the very bottom all the way to root node. Okay, so start from bottom to root node. That's when we do balancing, okay, balancing. So to get to the node, you just call array list, okay, get. Okay, so this is just like arrays indexing, is it a similar concept, okay? And okay, and if it is not the root node, is it? Because when I is 0, it's a root node, is it? It's a root node. So how do we do the balance? Whenever you do balance, we also need to take a consideration of the parent node. So this is parent node. Parent node. Okay. So how about probably I need to draw at least part of the tree. Okay, so that we can kind of understand how that works. Okay, so how about let's still draw that 55 and 40 and 42 and 38, 39. Okay, and this is 35. Okay, and here just assuming it's going to be updated. Okay, okay, so we get the node. Is it? We get a specific. Suppose it's this node. This is X. X. Is it? And who is going to be Y? And the Y. Then this is going to be Y. Is it? It's a parent node. Okay, it's a parent node. And then what we determine is we want to determine if Y's left is, if Y is left, so it's left, is it 38, is X. So in this case, it is, is it? So you are going to set the left as false, is it? Okay, and then we also use a pre-X to remember. So now this set as pre-X, also 38. Okay, and then we are going to do what? We are trying to balance X. Is it? And if you recall, when you balance, then it involves changing. As it involves changing. So maybe 35 is not a good example. Let's see, how do I do that? Maybe just assuming like this, like the tree. Let's see, how can I consider? So how can I consider? So assuming it's not balanced, because right now it's balanced. Okay, right now it's balanced. So assuming it still has some nodes. Okay, it still has some nodes. And then it's not balanced. Is it? If it's not balanced, then 39, then in this case, it's going to be switched. Is it? So what you will find this balance X. So basically it's 39. Is it? So X is going to be 39. Is it? Pre-X, 38, it's going to be pre-X. Is it? It's going to be pre-X. And if it's pre-X, it's not X. So that means balance happened. Is it? So this balance may happen and may not need to happen. Is it? So depends on if the pre-X is still that X, is it? So in this case, it's not, is it? It's not, then in our case, because it's not the left case, it's going to go to this case, is it? So Y's right, is it? Y's right is, that's not, this is not a good example, okay? Because if I draw like this, this should not be Y, okay? So so Y shouldn't be this 40, okay? If we have this kind of tree, so that's not precise, okay? That's not precise. But anyway, so what it means? Oh, that's right. Oh, yeah. So this is still Y, is it? Y's right is what? Y's right is 38, but okay, I'm sorry. Let's see, use this color. So Y's right, so so 40 basically, 40 is parent of 38, is it? And the 38 is that impacted node. Impacted node is that unbalanced node. Unbalanced node. Is it unbalanced node? So this is balanced node. Balancing node. After you balance node, generally speaking, what we need to do, you need to reconnect to parent node. Is it? So yes, Y's right. Is it Y is parent? It's right. It's going to be 39. Is it? So you're going to get 39 here and 38 move down and then 35. Is it? Something like that. So then you balance this node. Is it? So here it involves how do we apply what we discussed before for balancing the node. And when we do balancing, it involves left rotate or right rotate, is it? But don't forget, so this part of code is to reconnect parent node with the new balance node. New balance node. As to the other part, this balance method already taken care of. Okay, so we don't need to worry. Okay, so after we balance the node and also connect to its parent, that's not, you cannot stop that, is it? You also need to update all of the height, is it of the height from the parent node, is it all the way? Because the node itself, the height already be taken care of, is it? So that's why it's from the parent node, okay? Update from, so basically it's parent node. And to root, you also need to update height. Okay, update height. So this is the case along the path that's not the root node. Okay, not the root node. And when it reaches the root node, you just first need to remember the previous X, is it? And then you need to do the balance. And over here, because over here, this part is just, when I do my code design, I just try to do some debugging stuff, okay? But because it's a root node doesn't involve parent node. So basically, you don't need this, is it? You can just directly just call balance, is it? But here I just try to do some other checking, okay? So anyway, so when you call balance, then it's going to balance the root node and reset. If you recall the balance method, reset root to be, is it? Yeah, so anyway, so this is you balance the specified node, that is the whole path whenever a node is inserted or deleted. You're going to call this balance path method. Okay, then next let's take a look. So this is all just some side method. And what is the next one going to deal with is insert, is it? And for insert over here, be careful because it involves the node balancing and keep track of the path, is it? So that's why I have an array list created for insert, okay? And then each time you need to add your searching path, is it, to this array list, is it, to this array list? Okay, so that's how you log the path for insertion. Okay, so nothing new. Everything else just the same as what we do in the past for insert. You go to left or go to right. Okay. Nothing new. And after that, and of course, keep this in mind, okay? Binary search tree, okay? It doesn't allow duplicates, is it? So if some item is already in the tree, then you don't do insert, okay? You don't do insert. So that's why we can also use the tree for our set, is it? And map. And generally speaking, map's key is also unique. Okay, generally speaking, we don't allow key to be duplicated, is it? Okay, and then next, let's see. Then this part is you just add the new node. You need to create a node, is it? And you connect it to the parent node. Okay, that's from the path. And then what we do is we need to update all of the height, is it? After along the path, is it? Along the path, you need to update the height. Then after you update height, you balance of the nodes. Okay, so be careful. Update height first, then balance node. And when you balance the node along the path, it involves update height again. Is it? But here is because you add a new node, so you need to update the height. Is it? So that's after that, you update, you balance all of the node along the path. Okay, and for all of the other nodes, you don't need to do the balance. So that's regarding insertion. But like the case that we just discussed, is it, and some other tree. And here I didn't do the boundary condition, okay, to improve the code efficiency, okay. And in this case, basically, you don't need to do this part. You don't need this part, is it? Both of this basically no need, is it? Because the height, all of the height is already but you still need to update the height of this newly added node, is it? But of course it's 0, as it is 0. And 38 and along the path, and then 40 is of it. So no update needed, and it's already balanced, is it? So in this case, we can skip this 2 step, is it? But then we need to add some code, okay? Maybe that's a good exercise for you, okay? So anyway, there's some boundary condition, is it? And we can deal with it so that you can save some time, okay? Okay, and the insert 2 is, so the way we just discussed, this is iterative way. Iterative approach for insertion and balance, okay? For insertion and balance. And then we need to do what? We use array list, use the path. We use the path. And there is another recursive way, okay? So this second is recursive way, and we will later on discuss, okay? And let's first move to delete. Okay, the delete algorithm, it's exactly the same as what we previously discussed, okay? Nothing new here. And then you find, then we already know that, is it? And the only new thing we need to change is, first, we need to have a path, is it? So whatever the node is deleted, we need to find the path from its parent all the way to the root node. So that's what we call here get path, okay? Because you need to update, is it? Then same thing as the insert. You need to update the path height. You also need to balance the path, is it? So this too the same for the as insertion, but over here, how do you get a path? Is we just need to get the path from the parent node, okay? And then let's see, how do we get to the path? Okay, get path. So here we have that get path. So you specify a node, is it? And you're going to return that array list. So you start with the root node, is it? And for each of it, you just, when you do the traversing, is it? You just add the node to the path, is it? And this is just like you do the search, is it? It goes to right or goes to left, is it? And when you find it, then you just return the path, is it? Or you return the whole path, is it? So that's for the get path, okay? After you get a path, then you can update all the heights along the path, all of the nodes height, and then you rebalance the path, okay? So this is for delete, okay? Also, not a lot of new things. And then next, let's take a look at the recursive way. Okay, you will see the recursive way for insert and delete, and also here, balance, is it? It's much simpler than the iterative way, okay? So let's take a look here. Okay, and when we do insert, you can just call, we have a utility method called insert node. Okay, and whenever we want to insert an I, we always start at root node. That, so we call insert node with root, and this is the item you want to insert. Is it you want to insert? And logically, if you recall, when you do insert, you kind of need to first along the search path. Is it? Search path, whenever you reach the leaf node, is it? That means that's the place you are going to insert. Is it? That's the stopping case. And the insert node is a recursive method. Recursive method. Is it? That's why when it reaches the leaf node, is it? So this is the stopping case. Is it? And it return the new node. Is it? Create the new node. Okay, so that's okay. Is it? And of course, if the item is already exist, then you just return that node. Is it? So okay. So this two case already taken care of. Then you just kind of like search. If it's less, then you should go to left. Is it? And did you see it's very smart here? You just call insert. Insert what? The nodes left. Is it? The nodes left. And with the item. Otherwise, you just call insert. Recursive call insert right. Is it? And with the item. Is it with the item? And after you finish insertion, is it? Did you see you update height? Is it you update height? Then what do we return? So that's so the insert node does return. Is it? So it return wherever the balance needed. Is it? And just think about along the path. Along the path, the insert will keep balancing. Is it? Will keep balancing. So the parent node is going to be connected with whatever after you do left rotation or right rotation, that B node is going to be bring up. Is it? It's bring up, then it's, so basically that's the B. Is it? And then it's connected to parent node. Is it? With this recursive call, it automatically taken care of. Is it? So that's the smart part for the recursive implementation. Is it? Because it also called the balance. Is it? And anyway, the balance return is that new balance node. Is it? And then this part taken care of. Is it? And the height also along the way, when you do recursive call, it's going to be updated. Okay, it's going to be updated. So that's how the recursive way implementation works. And if you, I recommend you, if you want to trace, you can draw a call stack. If you draw the call stack and with a tree, you will understand this recursive way implementation better. Okay, so that's you can try it. Okay, so this is a recursive way to do insertion. Okay, and the same thing for delete. Okay, you can also implement with a recursive way. So then here you want to delete some item. Is it? And of course, we use a auxiliary recursive method called delete node. Okay, delete node. Then let's see. For the delete node, what it does is similar, is it? So if it's less, then you go to left. If it's high, you go to right, is it? And you reconnect with the parent node, is it? And why we can do this similar concept as insert, is it? Because anyway, you're going to update height and balance the node along the path. And whenever you do the node balance, it will return that new balance B node, is it? And that part, and this part will be taken care of the connection to its parent node. Is it connected to its parent? So this part purely taken care of, is it? And okay, and this is the case, is the node to be deleted. Is it node to be deleted? Node to be deleted, did you see? Because this delete node return the node. Is it return the node? So what is it says? Okay, if the node you are going to delete, if it's left is a null, then it's going to return what? Return its right. Is it? And because it's return right, and then later on, then it's just directly connected. Is it? So let's see, how about this case? We have that 40, we have that 38, then 39. Is it? So suppose we want to delete 38. Is it? And its left is now, you return what? So you return 39. You return 39. Over here, you said, I want to delete that node. Is it? And it's a return what? Return 39. And it's get connected with what? With this. Is it? So then it's get connected to the parent. So this is gone. Is it? And if it's a leaf node, it's the same thing. Is it? And if it's a leaf node, then it's just a null. Is it? So this part taken care of, delete a leaf node or a single branch case. Is it? To take care of both of this case. And also taken care of, automatically taken care of by the reconnection. Is it? Connect with parent node. Okay. And this is the case when a node has two branch. Is it? Has two branches, then if you recall, you need to find its next in order node. Is it? If you recall, you need to find its next in order. And find its next in order, it's the recursive way. Is it? Recursive way. Then you can find the next in order. Okay, so how about we can draw that case. It's 55. And here is that 40, and here we have 62, is it? And 58, 70, is it? And here is 57, 60, and blah, something, okay. And for the 70, under 70, we have 64. After 64, then I have 63, 65. Let's see. Okay, that's it. Okay, and suppose the node you want to delete is 62. Is it? And for 62, what's the case? You need to find the next in order. Next in order successor. Who is it? It's this one. Is it? Then we are going to swap these two. So 63 move here and 62 move down here. Is it? So that's how you find the next in order. Is it? find the next in order, then you are going to do what? You need to reset its left and right. Is it basically 63? 63, its left is what? Is a previous. So this is y. Is it? You also let y remember. And the y's left is what? Is 58. Is it? So this part taken care of. And then how about this part? Okay, this part is supposed to connect with 70. Is it? And with 70 here, it involves a case. You need to find the next in order. Is it? Find the next in order and also delete it. That's why we have a method called next in order and delete. And what this will return, it will return this subtree. Is it? Return node 70. So that's why node 70 then reconnected with 63. Is it? And this part will be taken care of by this delete next in order method. Okay, that's the whole logic here, okay? And then if you recall, and this delete next in order, it's the same thing, is it? It just find the next in order, then delete it, is it? And at the same time, you need to update the height and also do the balance because it involves delete, is it? So that's that left in order, that small subtree part, okay, you taken care of, delete, okay. So here it just shows we can also use a recursive approach to implement insertion and deletion, okay. Okay, so that's